The purpose of this video is to continue the work on successive ionisation energies. You'll need the study pack to complete the tasks, so you'll need to download a copy of that. What we looked at in the last video was the idea that it becomes more difficult to remove each electron from an atom. So obviously, when you try and take the second electron off, it's more difficult than the first. The third's more difficult than the second, and so on. However, it's not a nice, simple, straight line. It becomes more difficult to take electrons off, much more difficult, if you move from one energy level to another, which is much closer to the nucleus. So what we've got here on this graph is looking at how successive ionisation energies provide evidence for the arrangement of electrons in energy levels or shells. So the first, second, third, fourth and fifth electrons in this example must be in an energy level further away from the nucleus than the electron, the sixth and the seventh electron, which must be in a shell much closer to the nucleus. And so what we're looking for in terms of evidence about atoms and arrangement of electrons is, where is there a big jump between one ionisation energy and another? And we can clearly see between the fifth and the sixth there is a big jump in ionisation energies. So it's telling us the first five are relatively easy to remove. They must be in an energy level or shell further away from the nucleus. Whereas the sixth and the seventh electrons, those ionisation energies are much, much higher, dramatically higher. So they must be much more tightly held by the nucleus. So they are in an energy level much closer to the nucleus. So when you're looking at data, what you are looking for, however it is presented to you, is where is the big jump in ionisation energy? Where is the biggest jump? That will tell us when we're moving from an outer shell into an inner shell. Or perhaps even, if there are two big jumps, the innermost shell. Okay. So looking at that graph, it's showing us that there are 5 electrons in the outer shell. If we are told that this element is in period 2, obviously what you're then going to do is, which element is in period 2 in group 5, and clearly you would expect that to be nitrogen. Oh. Must be in group 5, and it must be nitrogen. There we are. So looking at the graph, see if you can think about what the missing words would be in these paragraphs. The large increase in ionisation energy between the fifth and the sixth ionisations shows that the sixth electron has been removed from a different shell. Is that closer or further away from the nucleus? Clearly it's going to be closer to the nucleus. Big jump means it's getting harder to pull the electrons off because they are closer. What we have noticed is that there's a gradual and steady increase in the energy needed to remove each electron, even within the same energy level. So each successive ionisation energy is greater than the one before. Now there's different ways to think about this. We could think about, well, clearly it becomes more difficult to pull the electrons off because you're pulling them off an increasingly positive ion. Another way to talk about it is in terms of the proton-electron ratio. Think about the number of protons and think about the number of electrons that are currently on the ion. As you pull more electrons off, the electron number decreases. So the proton number will always stay the same because you're not doing anything to that. But as you increasingly remove the number of electrons, the electron number goes down. So the proton number divided by the number of electrons, that ratio will increase. Think about it as an equation, protons divided by number of electrons. Well, if the number of electrons gets smaller, any number divided by an increasingly small number, the answer to that will be bigger. So the proton-electron ratio increases every time you remove an electron. The number of electrons remaining is less than the number of protons in the nucleus. The nucleus attracts the remaining electrons more strongly and draws each shell closer to the nucleus. So more ionization energy is needed to remove each successive electron. So two different ways of thinking about it, either in terms of the proton-electron ratio or as a more general description of how it becomes more difficult to remove electrons from ions which have an increasingly positive charge. Okay, what you now need to do is turn to the student exercise. You're going to work through this. So we're going to pause the video, giving you time to work through it. When you set the video going again, I will obviously start going through the answers. So you may, if you're confident, try and work through all of the questions. Alternatively, have a go at the first couple, rejoin the video. I'll show you how I've worked through them. You can then repause the video, attempt the remaining questions, and then obviously come back to me to find the remaining answers. So pause the video now and rejoin where you feel the most confident. Looking at the answer to question number 1, what we're looking for from the table is where is the biggest jump in ionization energy? And the biggest jump, the biggest difference between any of the two numbers is between ionization energy number 2 and number 3. So that tells us that the first two electrons are relatively easy to remove, whereas ones which come after that are much more difficult to remove. Now clearly you've always got to think about arrangement of electrons in energy levels. So we're looking for the first two being relatively easy to remove and then the remainder much more difficult. So the first two can come off, which means 2 electrons in the outermost shell. So that is going to be a group 2 element. And what we need to do is say that the biggest jump in ionization energy is between ionization energy 2 and ionization energy 3. And that tells us that we've got 2 electrons in outer shell. Was that effect? Now I've obviously simplified this in order to make it faster just by writing IE to represent ionization energy. Really, you need to write that out. Now we've got a similar issue here. We're looking in question 2. Where is the biggest jump? And I can clearly see around here we're going from 4,356 kilojoules per mole to 16,091 kilojoules per mole. That's the biggest jump. So that is telling me that these electrons, the first, second, third and fourth ionization energies, they're the lowest. And then what comes after that, those electrons must be in a shell closer to the nucleus. So the first 4 are easy to remove. So it's telling us that element Y is in period 3. We're looking for an element, a group 4 element, as a big jump between the 4th and 5th ionization energies. This is what the examiners are looking for, being clear about which group it's in, as we've got a big jump and saying where the big jump is. So 4 electrons in outer shell. I've not answered the question yet. It's telling us element Y is in period 3. So we're looking for an element, period 3, group 4. So if you find group 4 on your periodic table, in period 3, that's going to be silicon. Now in question 3, what you have to do is sketch a graph. Sketch. These don't have to be accurately plotted. You're going to sketch a graph to show the successive ionisation energies. Remember, the innermost shell, the first energy level, the one closest to the nucleus, can hold up to 2 electrons. The second holds up to 8, and so on. So aluminium, 13 electrons to remove. What I would suggest you do is think about the electronic configuration of the element. Well, for aluminium, we've clearly got 3 electrons in the third energy level, 8 electrons in the second, and 2 in the innermost. Now, the mistake that people make when they draw graphs such as these is we've been drawing graphs like this before, where we put electrons into orbitals in subshells and so on. And the 1s is down at the bottom. That's closest to the nucleus. Well, when we think about these graphs, we're kind of looking at it from the opposite perspective. The electrons which are easiest to remove are the ones which are in the outermost shell. So aluminium, because it's in group 3, has 3 electrons in its outermost shell. They're the easiest to remove. You then have a big jump in ionisation energy before you get to the second shell, where you've got 8 electrons, and then finally another big jump when you move to the innermost shell. So the graph would look like this. These are the innermost electrons. These are the outermost. Now, one way to help think about this is to go back to that GCSE knowledge that hopefully is still there, and think at GCSE you would have written for aluminium the electronic configuration as 2, 8, 3. Well, I can clearly see we've got 2, 8, 3. So hold on to that GCSE knowledge. It can still be useful. We don't always need to be thinking about 1s and 2s and 2p and all that business. Sometimes the simplest way of thinking about it can help us to get to the answer most quickly. So similarly, if we use that method on B for neon, well, neon at GCSE, the electronic configuration was 2, 8. So it's going to be 2, 1, 2, 3, 4, 5, 6, 7, 8. These 8 electrons are in the outermost shell, and these 2 are in the innermost shell. Again, similarly, if we take that GCSE model, okay, magnesium we know is 1s2, 2s2, 2p6, 3s2, or 2, 8, 2. I think the GCSE model is going to help us the most here. So I've got 2 electrons on the innermost shell, 2 electrons on the outermost shell, they're the ones I've just circled, and then we've got the 8 electrons on the second shell. Phosphorus, atomic number 15, well, innermost shell, 2 electrons, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. Make sure you give yourself enough room in the exam if you're asked to sketch one of these. 5 electrons in the third energy level, the outermost. easiest ones to remove. 8 on the second energy level, 2 on the innermost, the first energy level. We need to make sure that we're showing that the ionisation energy is gradually increasing as we remove each successive electron from each energy level. And then we're looking for big jumps as we go from one energy level to an inner energy level. Okay, what you now need to do is have a go at the homework assignment. Try those questions. The mark scheme will be provided. Hopefully, if you've understood the examples we've been through, they shouldn't be too problematic. But you do need to remember, learn that definition for first ionisation energy.